thank you again for giving me the opportunity to present here at this Wavefront Congress. It's a great opportunity for us. And so as Genuer says, so I'm Valentin Genuer, and I work for Physics Corporation. And the idea of this talk today I wanted to give is to first provide an introduction and a description of a new kind of wavefront sensing technology that I will pose as an alternative to classic and standard way to measure the wavefront distortions. And in a second phase, I wanted to share some applications that are already in use for this technology, but also share with the attendees and also the panel here some insights of where we could use this technology and where it could be useful. So my presentation will be as follows. I will first go very quickly on the company itself, Physics. Then I will go into details on the technology that we use, that we patented, and then go further on the applications, and then maybe the most interesting parts, which will be the discussion. All right. All right, so Physics, very quickly, our core competency is to measure the wavefront distortion, so the wavefront of light, so the spatial phase distortions of a beam or an optical systems. So to do this, we manufacture wavefront sensors that you all know. It's a compact camera that measure the wavefront distortions, but we also do machines where we integrate the wavefront sensor to measure optical properties of optical systems. So the company patented this technology, which is called quadri-wave lateral shearing interferometry. So I will go into details on this technology further. And it's a spin-off from two French laboratories. So the company is based in France. All the R&D, the production is in France. And I work for the US branch in San Francisco, California. And historically, what we do is basically measuring the wavefront aberrations of laser systems, like the one you could find in Nebraska, for example. Ron mentioned this, like the Extreme Light Laboratory at the University of Nebraska. And basically what they want to do is measure the wavefront distortions of a laser system, high power or high energy system, and correct the aberrations using an adaptive optics loop, using a deformable mirror, for example, to correct in real time the aberrations. So historically, this is what we do. We measure the wavefront aberrations and we correct them to provide the best wavefront possible. So the company was created in 2003, and basically we have clients worldwide, either in academic or industrial applications. We cover a very broad and varied range of applications, ranging from optics metrology, so measuring the optical aberrations of optical systems, either for consumer electronics applications, you can see here, either for the automotive industry, but also for national laboratories measuring the aberrations of high power laser systems, as I mentioned just before. So let's go into details about the technology that we use. So it's called quadri-wave lateral shearing interferometry. And basically, it is an evolution of the standard Shakatman technology. So you are, I'm sure, familiar with the Shakatman technology, which uses a grid of microlenses in front of a detector, so mostly a simple CCD camera. And basically, they will look at displacements of focal spots on a detector. So if you have a perfect plane wavefront, the location of the focal spots of the different lenses are at a central location. And as soon as you have distortions in the wavefronts, you will spot a displacement of those focal spots. So what we use is a modified HARMAT mask. So there is no more microlenses. It's a two-dimensional diffraction grating that is positioned like a Shakatman sensor in front of a detector. But what we will be looking at is interference fringes. So it's a small and compact, very compact interferometer that we are using here. If we go into details, so it's a lot of words, but every word matters. here. So if you take the example of a diffraction grating in 2 dimensions, so it's a grid of holes, and you put a screen very far away, a few meters away, if you shine a collimated beam, you will generate orders of diffraction. So the 0 in the middle, the plus and minus 1 in 2 directions, and so on. So it's an example if you put a screen very far away. However, the diffraction grating that we use has been specifically designed to only keep the 4 first orders of diffraction. And the basic idea is that everything is enclosed inside a camera. So the detector is very, very close to the diffraction grating, which leads in the end to creating interferences between both orders of diffraction. So in the end, on the sensor, you have this pattern here, which is an interference pattern created from the interference from 4 replicas of the incident beam. So it's a combination of replication of 4 waves. So it's basically a replication of 4 beams that will interfere on the sensor. And if you have a perfect beam, you will generate a perfect interference pattern here, a perfect grid of interference fringes. And if you have distortions in the wavefronts, you will generate distortions in the interference pattern. And this is what we care about here. Basically, once we have this interference pattern on the sensor, we will do some post-processing using Fourier transform to track shifts in spatial frequencies. So this is a raw interference pattern that we have on the sensor. Then we go into the Fourier space, and we will basically look at distortions of the spatial frequencies here. So if you have a perfect beam, again, no aberrations like a flat planar wavefront, you will have perfect peaks in the Fourier space. But as soon as you have distortions in the wavefront, you will start to generate harmonics around the main frequencies peaks. And this is what we care about again. So this is the basic idea here. And again, the idea to retrieve the full wavefronts is to go into this Fourier space, have 2 different deconvolution windows that will provide us with the gradients of the phase. So it's basically the phase derivatives, and that we will then combine and integrate to get the final full phase map. So it's basically like a Shack-Hartman wavefront sensor. We'll have the phase derivatives, so the gradient of the phase map. But here we will also have the intensity map, which means that in one single measurement, and the processing is real time, we'll have the full phase map and the intensity map. Now, let's move to the advantages of this technology compared to a Shack-Hartman sensor. So the first one, and the most important one, I would say, is the high resolution. Because the number of measurement points of a Shack-Hartman sensor is linked to the number of microlenses you have in front of the sensor. Here, with our technology, we basically use 4 pixels on the sensor to sample the fringes, which in the end can lead to sampling and resolution of more than 800 times 700 measurement points, where with a Shack-Hartman sensor, you can usually go from 32 times 32, or the maximum is usually around 100 times 100. So it's way more measurement points that reduce the uncertainties on the estimation of the Zernike aberrations, for example. And also the spatial resolution is much, much smaller, can reach under 20 microns in terms of spatial resolution, depending on the magnification system. The second one is the large dynamics. So it's pretty useful when you want to measure an optical systems that is generating very large aberrations. Even if it's just pure defocus, pure power, we can use the wavefront sensor in the beam path with no relay lenses to measure this high curvature or very large dynamics wavefront distortions. Another advantage is that it's not sensitive to intensity modulations, because we do not care about spot displacements. We just care about spatial frequencies. All the analysis is done in the Fourier space. And the last one is that the technology itself, as it has been designed, so it's by design, it's achromatic, which means that the measurement itself does not depend on the wavelengths you are using. There is no calibration when you change the wavelengths of illumination, and you can also use broadband sources. So it's all those four advantages: the resolution, the dynamics, the achromaticity, and the insensitivity to intensity modulations. If I go back on the applications, so the first one is measuring the aberrations of laser beam laser systems doing adaptive optics. The second one is measuring the optical properties of optical system, which is just eyeglasses, complete optical assemblies, or just contact lenses, IOLs, measuring the aberrations, so the wavefront error, but also the MTF, so the modulation transfer functions, and everything else. And the other application is what we call imaging. It's basically using the wavefront sensor as a tool to measure change of refractive index in a material. Let's say you have a contact lens where you want to embed a metastructure to generate an optical function, or even to basically just induce change of refractive index with a femtoseconds laser, for example. You can use the wavefront sensor to precisely measure the change of refractive index with a very high spatial resolution. And now it's more discussion, and I wanted really to share some insights here today on where these advantages could be useful. So it's a fact that high resolution wavefront measurements provide more accurate estimations of high order wavefront aberrations and also change of refractive index. And it's a fact because we have more actual measurement points. It's not like a Shack-Hartman where you could fake a high resolution by using post-processing algorithms. Here, all the measurement points are actual and real sampling measurements of the wavefront itself. So it already finds application in manufacturing, control, and R&D for eyeglasses, contact lenses, IOLs. Either a new generation of lenses with, as I mentioned just before, metasurfaces, where you basically want to provide specific optical functions that you want to embed in the material, and you want to make sure that you know very precisely the change of refractive index, but also measuring the optical properties of next generation of AR, VR, and MR systems. And then this technology could maybe find application in other fields. For example, the research and development on new aberrometers or vision correction devices, and maybe also enhancement of current refractive surgical techniques. And the basic idea is that, and the main question would be, when is the resolution really important? Measuring higher order aberration, as we know, seems to provide better results in patients. So correcting for these higher order aberrations seems to provide better results in patients. But when enough is enough? So is measuring even higher order aberrations is something that could be useful? Are there requirements for more sampling, either for wavefront guided refractive surgery techniques, or either just for the characterization of the correction devices? Those are really just insights and discussion points that could be applied to just the audience or the panel here today. And this is what I wanted to let and share with you and today. And I think that's pretty much what I wanted to share today with you. Thank you for your attention.